Alright, so the following is number 20 on page 318, and it was asking, it's basically the scenario is a horizontal spring with a mass, has a stiffness of 200 newtons per meter, mass of 0.4 kilograms, and gives an initial spring compression of 0.1 meters and an initial speed of 3 centimeters. And it's asking the maximum stretch during the motion, maximum speed during the motion, and then the power input required as the spring dissipates 0.01 joules for steady oscillation. So firstly, what is the maximum stretch? To find the maximum stretch, well, actually, let's go to the diagram. So we have a spring, and it's already initially compressed 0.1 meters. As soon as we let go, the spring is gonna jolt up to the right, or whichever direction being pointed, and it's gonna reach its final trajectory, and so the y final, so the final height. At that instance, velocity will be 0. So we can assume that at its greatest point of distance in the x component traveled, I guess, the velocity will be 0. So if we use the equation W equals change in kinetic energy plus potential energy, we'll get that the final kinetic energy should cancel out, and we want the maximum stretch, I believe, right? So we can solve for SF. The main component that from this picture was that at this greatest, like I mentioned before, at its farthest distance, the velocity will be 0. Okay, and we get S equals 0.1673 meters. The second part is what is the maximum speed during the motion. So we said that at its farthest point, the velocity is 0. So if you think of in terms of physics once again, as soon as you let go of a compressed spring, it's gonna just expend all the energy compressing that spring, and it's gonna push whatever way is being compressed. So the greatest speed will be as soon as you let go and it's released. So to find it, we use the same equation once again, where W equals change in kinetic energy plus change in potential energy, and we get the VF is 3 meters per second. So that wasn't too bad. The third part was the energy dissipation of 0.1 joules per cycle, and we had to find the input in watts to maintain a steady oscillation. So the book gave the time period was angular frequency as square root of m over k. Now if you multiply that by 2 pi, you will get t, or sorry, t equals 2 pi over m square root of m over k. We have both mass and the spring stiffness. So it takes 0.2809 seconds, and it wanted, I believe, watts. Yeah, it wanted watts. So watt power, which is power. So power equals energy over time, and you get the units of 0.0355985 watts. So from this one, I think it just wanted us to have a keen understanding of power.